Hello my dear students, this is Akash HD. Welcome to the ASD physics classes. Hope so you all are doing really great. So students, in this video we are going to learn the Ampere Circuital law. We will solve some questions. After that we will learn the applications of Ampere Circuital law. That means how this Ampere Circuital law is useful to calculate the magnetic field of some symmetrical situations of the current, like a magnetic field of thin wire, thick wire, hollow wire, and in next video we will see due to solenoid, toroid, and so many questions based upon that. Okay, so let's start the video. So here the topic is Ampere Circuital law. See here kindly, this law is an alternative form of Biot-Savart's law. Okay, alternative form is there for Biot-Savart's law, because you know very well Biot-Savart law is also used to calculate the magnetic field, and Ampere Circuital law will be also useful to calculate the magnetic field. But when the some symmetrical situations will be there, in that situation we will learn all these things. Okay, so see now, this law is very important for the exam point of view. You have to write, according to this law, the line integral of magnetic field around an closed loop in free space, we can tell vacuum, is mu naught times of net current enclosed by that loop as shown in diagram. Okay, and what is mu naught? This mu naught is called permeability of the free space. In SI, its value is 4 pi into 10 to the power minus 7 SI unit. Okay, now after that here, if we want to write this law, okay, see here, diagram is there. So remember that here, this is called the Amperian loop. What is this? This is called here the Amperian loop. Amperian loop, here imaginary line, so I have drawn with the dotted. Even in some books they can draw in a solid line also, not a problem. Okay, and what we'll do here, this Amperian loop will have some direction. Okay, so what I have taken here, this direction I have taken like this, for example, anti-clockwise. Remember that, very important, when the direction of Amperian loop, what I am telling, when the direction of Amperian loop is similar to the magnetic field direction of respective current, then enclosed current will be taken as positive, otherwise it will be taken as negative. What I am telling, again listen, when the direction of Amperian loop is along the magnetic field direction of the current, okay, then only it will be taken as a positive. Okay, so see, for example, here I have taken here which direction? Anti-clockwise. Okay, so mathematically if I write here the Ampere Circuital law, we can write here the closed integral. Which one? Line integral. Here you can write even L also, but no need as of now. See, B.dl, closed integral B.dl is equal to mu naught into I enclosed. Okay, mu naught into I enclosed. Now this thing only I was telling you how to take this enclosed current. Okay, so you can see very well, Amperian loop I have taken anti-clockwise. If I take the I1, all my fingers along, see, this thumb is along the, because one thing remember that here, whenever any wire is there, straight wire, magnetic field due to that will be concentric circles. What will be there? If in case there is one wire carrying current I, then what will be there? How the magnetic field lines will be? It will be concentric circles like this. Now magnetic field lines will be what? Concentric circles, even that you have seen in 10th also, is it? And here if I see, let's take this current I is along the, this current I is along the y direction, then this concentric circle in a which plane? ZX plane. What I am telling, if this current in y direction, then this concentric circles of magnetic field were along ZX plane. Okay, and the direction like this here, is it? My right hand thumb rule. So in the same way, what I am telling that here, see, my thumb is along the current, and if I curl my finger, so you can say due to current I1, curled fingers is along the Amperian loop direction, so this I1 will be taken as positive. If I take this I2, that means cross means current is going inside, and then you can see my curled fingers in the opposite direction of Amperian loop, so this will be taken as negative. Similarly, if I take I3, so see, I3 current is coming outside, thumb outside, all the curled fingers along the direction of Amperian loop, so that will be also taken as a positive. Okay, but by default remember that here, whenever it is anti-clockwise direction, outside current I will take positive, and this inside current, that means I2 will be taken as negative. If I make it reverse, that means if this Amperian loop is in clockwise direction, then what will happen that here, this I1 and I3 will become negative, and this I2 will become positive. Okay, so remember that here. And this outside current I4, I5, I6, they are having not at all effect if in case we want to calculate magnetic field here, let's take a magnetic field in this direction, B, okay, and dl also we will take in same direction. Is it like this, B dot dl, okay? So this I enclosed will be how much here? See here, this I enclosed is given by I1, current is outside, plus I3 minus I2, is it? So I1 plus I3 minus I2. When my this Amperian loop, in which direction? When this my Amperian loop in a which direction? Anti-clockwise direction here. Is it? Again I'm telling you, this is enough, but if in case something we want to learn in a much more basics, so here, this I enclosed current, I can write here, see, minus I1, minus I3, plus I2. When this Amperian loop, it will be in a which direction? Reverse direction, clockwise direction. Now that means all the roles will be interchanged here. Okay, so kindly see how we have done this. Is it? Enclosed current calculation is the very, very important. Okay, but by default 99.9% cases what will be there? This Amperian loop we will take in anti-clockwise direction. Outside current will be positive and inside current will be negative. Okay, great. Now students, after that we are going to see some important points regarding Ampere's law. So see the first point, this law is independent of shape and size of the closed loop named Amperian loop, similar to the Gauss law of electrostatics. Gauss law of electrostatics also independent of shape and size of the closed surface. So here also independent of shape and size of the closed loop. In Gauss law surface integral was there, but now here line integral is there. Is it? Now see second one. This law is applicable for conductors carrying a steady current, constant current, DC current, like that. Okay. Third one. This law is analogous to Gauss law. As I have told you, Gauss law of electrostatics. Why? Because this law is very suitable to calculate magnetic field of symmetric current distribution. Is it? Remember that here. Next one, in under the extra, we are just seeing the magnetomotive force. So remember that here, magnetomotive force means this MMF. This magnetomotive force, like EMF is there, na electromotive force, in the same way MMF is there, magnetomotive force, that is responsible for the generation of the magnetic field. So this MMF is given by, remember that here, closed integral H dot dl. And what is this H? This H is called a magnetizing field. What H is called? A magnetizing field. Remember, capital B is called maybe magnetic field, maybe magnetic induction, maybe magnetic flux density. That is B. But what is H? H is a magnetizing field. Okay. So now after that, see here, this you know very well, this formula, B equal to mu naught into H. I am telling in a vacuum actually. So this is the, we will see in the next chapter, B equal to mu naught into H. So what is H? H is given by B by mu naught here. What H is given by B by mu naught into dl. Then what will happen that here? This 1 by mu naught will come outside and closed integral we can write here B dot dl. Is it? And what is this closed integral B dot dl? See here. What is this closed integral B dot dl? This is the mu naught into I enclosed. So see 1 by mu naught, and here mu naught into I enclosed. So what will happen that here, the students? This mu naught and this mu naught will cancel out. Is it? So if I write here the MMF, hence MMF, we can write here, see, closed integral H dot dl. What this will come here? This is just coming here I enclosed. What it is coming here, the students? This is coming here I enclosed. Is it? See, remember that. Yeah, this is called magnetic force or MMF. Is it? ENC means enclosed. ENC means enclosed. Okay, great. Now see here, this basics required here. Now, so see, write equation for Ampere's circuital law for the Amperian loop traversed in the direction shown by arrow marks put on it. Okay, so this is the situation. So whenever we are writing the Ampere's circuital law, this we know very well, closed integral B dot dl is equal to mu naught into I enclosed. Okay, that means we can write here mu naught. The main story is there to calculate the I enclosed, which current positive, which current negative. This wires is along which direction? Remember that here, this wires is along the Y direction. Okay, because this basics I am following here by default, X mathematical, Y, and this is Z. If I am not telling anything, that means this basics I always follow. This all is perpendicular. Is it? This all is perpendicular. Now this I am following. So here what is happening that here now, which current positive, which current negative. Now let's take, if I talk about the current I1, so see you just see on this, focus on this now. So like this thing is there, see, like this, is it? So all the fingers along the current, you can see curved fingers is going along the arrow, that means I1 is positive, is it? Now after that, if you talk about this I2 and I3, again if you see for the I2, put your finger along the I2, then you can see the curved fingers is also going along the arrow, that means I2 also I will take it positive. I3, again put your fingers along the current, see all the curves are going in the opposite direction of the arrow of Amperian loop. That means what will happen that here, see this I1 positive, I2 positive and I3 will be negative. What I have told you again, if we put thumb along the current, then this curl fingers should go along the Amperian loop, then only current will be positive, otherwise negative. So again I will check one more time, this I1 positive, this arrow, this one will take here, again I2 negative, this I3 means reverse direction going negative. Okay, so I1 positive, again I am telling I1 positive because the magnetic field direction is along the Amperian loop direction. I2 is also positive because magnetic field direction is along the Amperian loop direction. I3 will be negative because magnetic field direction is opposite to the Amperian loop direction. So I1 plus I2 plus I3 here. Okay, so I includes how much here? I1 plus I2 plus I3. Is it? Great. Now students, let's see this question again. Here also we have to use the basics. For NEET and JEE, this question is important. So here what is the question? Kindly see here. Figure shows 4 identical currents I and an Amperian loops encircling them. We shall calculate in the direction marked the correct value is. Okay, so this thing is given here. Okay, so again this Ampere circuital law means closed integral B.dl is equal to mu naught into I enclosed, ENC I enclosed. That means mu naught. Again the story will start here. Okay, so now I will start one by one. Let's take, I have taken here current 1, current 2, current 3, current 4. Like this I am going to start here. Okay, so now kindly see the students, see my thumb is along the current. Again this wires in a y plane and this Amperian loop, this is called the Amperian loop, this is in a ZX plane. Okay, so see my thumb is along the current, then my all the fingers is going along the Amperian loop, that means this current I will take positive. Okay, now come to the second one. See here, this loop, now this loop is encircling this wire. Again you see all my fingers along the current, then curl fingers is going again along the direction of Amperian loop. This also I will take positive. Is it? Now after that, let's see here. See, you see here, my thumb is along the current and my curl finger is going opposite to the Amperian loop. That means this is negative. For this also same story, see my thumb along the current and see this my curl fingers is going opposite to the Amperian loop. That means this is also minus. So what we can write here? I, this is I, this current also positive I, but this current is negative minus I, this current is negative minus I. So what this will come here? It will come here 0. What it will come? 0. So closed integral B.dl is 0 where? This is there. Option B is the answer. Is it? Very, very important in the exam here. Okay? Great. Now students, after that we are going to see the applications. After completing the Ampere circuital law and 1 or 2 questions we have done, now we will see this one here. Application. So first application, what is this? A magnetic field of a thin wire. Okay, so see diagram is here, you can correlate. Let current I flows through a thin wire as shown in diagram. Magnetic field at a perpendicular distance. Which distance? Perpendicular distance R from the wire at point P can be calculated as here. Okay, so first remember that here we have the perpendicular distance. Now this distance is the perpendicular distance here. Okay, and let's take this distance is R now, and here I want to calculate the magnetic field here, and this is point P. Now again you can see very well it is looking like a maybe like a somewhat a flat shape, but this is the circle and this name is what? This is the Amperian loop. What loop? Amperian loop. Wire along this current carrying wire is along the which direction? Y direction, and this Amperian loop in a which plane? ZX plane. Okay, so see here, Remember that here, whenever we are doing the derivation, the Amperian loop direction, we will always take along the direction of the magnetic field so that this minus sign should not come. And angle between a magnetic field and dl will remain 0 degree also. Okay, so see, my thumb is along the current. Curl fingers is going which side? You can see inside. That means like this magnetic field is there, is it? So Amperian loop direction also I will take like this. Now after that here, if I write here the magnetic field, so see, just a tangent you draw here. This is the B, okay? And in the same direction, we will take very small length dl. Very small length dl. Is it? Again I'm telling, see, all the thumb along the current, see, my curl fingers like this. So magnetic field is like this. Amperian loop also I have taken in the same direction. Okay, or we can tell magnetic field of the current is along the direction of Amperian loop. Okay, so current will be taken as positive. Is it? So mathematically what we can write here, kindly see very well, as closed integral B dot dl is equal to mu naught into I enclosed. Is it? Now after that, see here, B and dl in which direction? Same direction. So B dot dl means B dl cos theta, and here cos 0 degree. Again mu naught I enclosed. How much current is enclosed in this Amperian loop? I current, and current is a positive. Is it? Current is positive, I have told you. Okay. Now after that, you know very well, if this is the wire, now, and here we are imagining one circle. So whether this point at a distance of r, magnetic field B, here also at a distance of r, magnetic field B, this side also at a distance of r, magnetic field B, this side also at a distance of r, magnetic field B. That means what will happen at all the points of Amperian loop, the magnitude of magnetic field will be same, constant. Direction may be tangential, but magnetic field value will be same, B will be constant. So B is coming outside, close integral dl is a mu naught I. Is it? After that, kindly see here, B closed integral dl means if we add all this small dl length, what we'll get? We'll get the length of the circle, and the length of the circle is called circumference. That means how much here? 2 pi r. Is it? And here mu naught into I. That means from here I can write here this B equal to mu naught I by 2 pi r. Now this is the formula. Even this formula we have done by the finite wire also in some specific cases. I have taught you finite wire, then I have taken some cases. There also we have seen that. So here what we know that here, remember that here this B is inversely proportional to r. What is coming? B is inversely proportional to r. Which graph will be there? The graph will be rectangular hyperbola. This side I have taken B, and this side r, the graph will be rectangular hyperbola like this. Remember that here, this side the graph should not touch B, this side the graph should not touch r. Which shape is this? Remember that here, rectangular hyperbola. Remember that. No, because sometimes they will not give the graph, they will ask only the shape of the graph. So rectangular hyperbola. Okay, mu naught I by 2 pi r. Is it? Now let's see here. Now after that, students, let's solve the question. Came in a NEET 2022. Important for JEE also. See, the shape of the magnetic field lines due to an infinite long straight carrying conductor is how much here? Okay, so here also what I have told you, if in case we have one wire, this wire anyhow carrying current I, na, in which direction? Na? Basic sign convention, mathematical. So this is along y direction. And here what will happen that here, if in case we will take the magnetic field. So at all the magnetic fields will be how? Magnetic field will be in a which plane? A ZX plane. Is it? Having the wire at the center. See, it is not forming correct, but okay, anyhow, what will be there? It will be concentric circles. Is it? See, now I'll try to do it as much as possible. Okay, like this. See, like this a magnetic field will be there. Okay, like this a wire will be at the center. Okay, and see here, thumb along the current magnetic field, like this it will be there, na? Like this. So see, center of the circles at the wire. Is it? If in case what will happen, the current is going in opposite direction, this magnetic field direction will get reverse. Instead of arrow like this, the arrow will get reverse. Is it? So what is this? Concentric circles. Where is the option? Plane, straight line, elliptical, and what is this answer? Circular answer is there. Is it? Remember that. Your thin wire. Even the same concept will be applicable for the thick wire also. Okay, circular magnetic field lines will be there. Okay. And one more thing. And you know very well, no? This B is inversely proportional to R, is it? So when we will go away from the wire, this R will increase, B will decrease. That means concentric circles are there, but distance between these circles will keep on increase. Why? Because magnetic field will keep on decrease. Is it? Because if circles are very close, magnetic field is stronger. If the circle is far, that means magnetic field is weaker. So as we are going away, magnetic field is keep on decreasing. That means when we are going away from the wire, distance between the circles will keep on increase. Remember that here. Okay, great. Can you see here? Is it? Now students, let's come to this one. As we have seen, due to the which wire? Thin wire. Now we will see due to the thick wire. Now derivation is not at all coming that much in a board exam, but the graph we will get, B versus R graph in this. Now that is the very important. Okay, derivation also may come, but mostly they don't used to ask. They may ask. Who knows? Magnetic field of thick wire. So see, let current I flows through a thick wire as shown in diagram. Magnetic field at a perpendicular distance small r from the wire at different points can be calculated as. Different point means outside, surface, inside, and all these things. Okay. So what is happening that here? Let's take now I have taken one point here. Okay, one point here, and I have given the name small a, small a. Capital A, B, C. Why I am not using? Because capital B means it will coincide with the magnetic field denotation. Okay. So this A I have taken. And let's take here this distance. Now this is all the distances will be measured from the central line of the wire and thick wire. That's why I have made it crossed here. Okay. And let's take here this observation point. This is here. This distance how much here? Let's take this one is having distance R. Okay. And if I talk about the radius of the wire is the capital R here. Okay. And what is happening that here? Current is flowing. Now current is flowing here. Current is flowing. How the current will flow? The current will flow through the area of cross section. Is it? Here current is there. Here you can see the observation point is outside. Okay, so if I talk about the area of cross section, see the area of cross section will be like this here, like this. Okay, and the current, see we have to take the enclosed current. That means area of cross section will be complete. Okay, so if I want to calculate the magnetic field outside the wire, basic is same, just like a thin wire. Okay. So see here, I will just write here as much fast as possible, B.dl equal to mu naught I enclosed. Then after that here, same story, B.dl cos 0. Okay, and why B.dl cos 0? Because current is going upward. This I will take here. This is the Amperian loop direction. Okay, then after that what will happen that here? The magnetic field, let's take like this. This is the magnetic field. B and DL also we used to take in the same direction, DL. Now like this. And magnetic field is also in the same direction. Magnetic field due to wire is along the Amperian loop, or what we can tell, I have taken Amperian loop in such a way so that the magnetic field direction is along the direction of the Amperian loop direction. Okay, so B.dl. So B.dl cos 0 mu naught full current I. This current I is passing through this full cross section. See this full cross section, total current I. So this cross section and this cross section anyhow same, because full thick wire is inside the Amperian loop. Amperian loop, this is the Amperian loop. Okay, so what we can tell here, mu naught, and how much current is there? I. Is it? Now after that what will happen that here, at a distance of small r, at all the points, magnetic field value is same. Maybe direction is tangential, value is same. So B outside dl is equal to mu naught I, and what this will come here? See, B, this will become here 2 pi r. Same story. Mu naught I, that means we can write here this B is given here mu naught I by 2 pi r. Okay, and this is where? This is the outside. B out means this formula we have to use here. Okay, and remember that here this B out is what? Inversely proportional to R. Okay, small r greater than r here. Is it? Same basic is same only. Okay, now after that students, if we talk about here at the surface what will be there? Small r will be equal to capital R. That means see the formula is B equal to mu naught I by 2 pi small r. So instead of small r, I will write here the capital R. Okay, and directly we'll get here the magnetic field where? At the surface. Is it? This too okay. But the main story starts when the observation point is inside. Here observation point was one observation point here I have taken here. Is it? Another observation point, let's take on the surface I have taken B, but now another observation point I am going to take when it is inside the wire, because the wire is thick. Is it? So can you see here? Now what is happening that here, let's take here itself, we will go here and see. Now the observation point is here. Now let's take here C. See, this observation point C is there. Now, and anyhow this distance how much here? Let me write somewhat smaller. See, again see this distance. This distance how much here? See, I am writing here small r here. Is it small r? Okay. And anyhow Amperian loop direction like this. Amperian loop direction like this. Now, and if I write here the magnetic field in the same way is there here also. This is the magnetic field B, and DL also in the same direction. Is it? DL also in the same direction. Okay. See. Now this is the DL, and this is getting somewhat smaller now, so only B dot DL in the same direction. Okay. So you know very well how much current will pass. How much current will pass? The current will pass through this cross section. See, I am just making here dotted now because space is not available. See, I am making here the dotted. That means current will pass through this cross section only, because this is the Amperian loop. What is this? This is the Amperian loop here now. Is it? So remember that here. Now the total current and enclosed current will not be I, it will be somewhat less than I. Okay. So see here this. If I write here the inside means what this will become here? See, as close integral B dot dl is equal to mu naught into I enclosed. Is it? So kindly see here, this one will be as it is. We can write here the B.dl cos 0. Okay. And mu naught, and how to get the I enclosed. I enclosed. Remember that here. Remember that here I will use the unity rule. What is the unity rule? Say here. When the area of cross section is pi r square, how much current is passing through it? I. Is it? After that, if in case the area of cross section of this Amperian loop, how much here? Pi is small r square. See here, this r is there now. So this area of cross section pi is small r square. So in this, how much it will carry? Remember that here, I by pi r square into pi is small r square. And this only is going to be how much here? I small r square by capital R square. In which one? In which area? Pi r square area. Okay. And this current is only which current? Enclosed current here. Which current? Enclosed current. Remember that here. Okay. And see, I'll just write here somewhere in like this here. Okay. Unity rule here. So now enclosed current, how much is coming here? Kindly see here. I small r square by capital R square. Is it? Both the sides as of now no. So CB close integral DL is equal to mu naught I small r square by capital R square. Is it? And this, what this will happen that here, this close integral DL will become here what? 2 pi r. Now the length of this Amperian loop 2 pi r, small r is there. Okay. So mu naught I small r square by capital R square. What will happen that here? See, this r and this one r is cancelled. Is it? So what this will come here? It will come here B equal to, remember that here, mu naught I small r by 2 pi capital R square. This one will come here. This is where? This is inside. Okay. And here remember that here inside means this B in is directly proportional to R here. Okay. Straight line graph here. Can you see? Very well. And we'll draw the graph also. Okay. So how the graph is looking like? See here. Let's take this is the center, central line. This is the small r equal to capital R. Most of the time wire used to be, the graph used to be in the first quadrant, but okay, symmetrical situation, I will draw here this quadrant also, minus r. So what will happen that here, if I will see here the graph, inside means it will be straight line here. What is this here, students? This will be straight line here, is it? So see, just as right here, see, this is straight line I have drawn here, even this side also, if you wish, see, we can draw the graph here. Now it should be somewhat as symmetrical as possible. Okay. After that, what will happen that here, outside the wire, outside the wire, see here, outside the wire it will go like this, like this, like a rectangular hyperbola outside the wire. So inside the wire, remember that here B in directly proportional to R. Outside the wire, what will happen that here? B out. What is this here, students? B out, inversely proportional to R. Same we can write this side also, but this graph is important, very, very important graph. See, center to surface, magnetic field will increase. After surface, magnetic field will decrease here. Okay, remember that here, this graph, very, very important graph is there. Okay, especially this first quadrant. Okay, great. Now students, let's see here, we are going to see this JEE 2023 question is there. So see the question is what? JEE 2023, same concept they asked NEET 2022 also. Okay, so see here the question. See, a long straight wire of circular cross section radius A is carrying steady current I is uniformly distributed across this cross section. Okay, uniformly distributed across this cross section means thick wire. Okay, thick wire is having the cross section, thin wire is having the negligible cross section. No, so the magnetic field is, you know very well what is the magnetic field I have taught you. See, I have taught you this is B, see this is R, no, like this, and here what is this? This is the surface. So what will happen? Center to surface. See, I will just change the different color. No, so see, center to surface, magnetic field will increase straight line, and after that it will go like this, is it? So when you will check out very well, the correct option is here, option C, directly proportional to R in the region R less than A. Okay, instead of R, what is this here? Instead of R, we can write here the radius is A. That's it, nothing different. Okay, I can write. So directly proportional to R in the region R less than A. Na? This region is what? This region is R less than A, and after that this region is what? R greater than A, is it? And inversely proportional to the R in the region R greater than A. Okay, so straight line and a rectangular hyperbola graph. Which option is correct here, students? Option C, important, thick wire. When they are telling current distribution across its cross section, thick wire only. Okay, great. Now students, let's see, one more question is here. No? Question, let's go through the question. JEE 2021 and even NEET 2021 also same kind of question came. So see the question, see, figure A and figure B shows two long straight wires of circular cross section A and B with A less than B, okay, carrying current I which is uniformly distributed across the cross section. See, again the told. Now, the magnitude of magnetic field varies with radius R can be represented as here. Okay, and see here, this is the figure A, radius is A, now current is distributed here. This is figure B, radius B, current is distributed here. And you can see very well, small a is less than B. So now, if we talk about here, see, the which graph is correct here? Now, so as you know very well, see, if I write here, see, this, if I talk about the magnetic field outside, first let's talk about the outside. No? Outside, what will come here, students? This outside will be inversely proportional to R. Outside what? Inversely proportional to R. At the surface, if I write here, the mu naught I by 2 pi R, is it? And if I talk about the inside it will be, see, mu naught I small r by 2 pi R, is it? So you can see very well, R is the radius. So you can see here, this B surface is inversely proportional to radius. What is the meaning? That means if the radius is smaller, what will happen? The magnetic field will be more. So here radius is small, here radius is bigger. So if I write here in terms of this, so what will happen that here magnetic field due to wire A will be greater than the magnetic field due to wire B, because radius of A is small, is it? Anyhow, where you can see here the magnetic field due to wire A is more, magnetic field due to wire A is more here, is it? So see here, in this situation also you can see magnetic field due to wire A, and here also magnetic field due to wire A. Now both the situations are existing, is it? And here also see it is existing here. Okay. Anyhow, this graph is not possible. So now three possibilities are there. This one we have got here. Maybe these three graphs are possible. Now see here, this is magnetic field due to wire A, and see here if I draw here, this is a magnetic field due to wire B. In the same fashion here also, in the same fashion you can see here also, this is BA, BB. Here BA, BB. Three possibilities are there. After that, you know very well, A is less than B. A is less than B. Radius is there. Okay. So if I write here, see, if I write here, here the students say, see here you can see very well, this is the A, that means this is R equal to A. Here R equal to B. So here you can see very well, A is less than B. But here if you will see here you will see here it is looking like in this it is A greater than B. Now that means wrong. Here also, here what is happening that here you can see A equal to B, because see both starting with the same line here now. So as A equal to B, wrong. Here what is happening that here, see this A is there now, so here we can tell R equal to A, here we can tell R equal to B. So they are telling A greater than B, but this is not matching with the question, so this is also wrong. But here what is this? Here we can tell very well, this B is here, A is here, so we can tell B is greater than A. That means correct option is here, option C is the answer. Okay, remember that. Like this we have to eliminate it. Okay, great. Now students, after that we'll see one more question. What is the question asked in a JEE 2020 and important for the NEET also. See the question. A long straight wire of radius A carries a current distributed uniformly over its cross section, again thick wire, the ratio of the magnetic field due to the wire at distance a by 3 and 2a respectively from the axis of the wire, that means the central line. Okay, so anyhow you know very well the what is given here, the radius is given a, radius is given a. Now after that, if we talk about here a by 3, so r a by 3 is there now, so r is the center to the observation point distance here now. So when it is given r equal to a by 3 and this is less than a, is it, that means this is the inside, okay, inside the wire. Similarly, if I talk about this one here, next one is given here 2a now, and 2a is greater than a, that means where this is outside of the wire, getting, because you have to compare with the radius, you have to compare with the radius. So this a by 3 point is inside and this 2a point is where, outside, is it, this is clear. Now after that here they are asking what, they are asking here the ratio. Okay, so see here I will write here the ratio B in by B out is equal to B in formula, inside what is the formula, see here, mu naught I small r squared by 2 pi capital R squared. Okay, now B out, what is the B out formula, see mu naught I, and see this will become reverse, so I will take here f 2 pi r here, is it, and why, see r and r is getting similar, so what I will write here, this is the r in and this is here r out. Okay, I hope so there is the not at all any confusion here. Now this is where, this is the inside and this is where, outside here. Okay, r in r out is there. Now after that here students, let's see what other things will cancel out. See this mu naught I is cancelled. Okay, and kindly see here this 2 pi and this 2 pi is also cancelled. So what is left here, kindly see this r in into r out by, it is coming here r square. Now after that what will happen at here, kindly put the values, r in how much here, a by 3, a by 3 into r out, how much here, r out is the 2a, is it, and capital R is the radius, small a, is it, so this is coming here. Now after that here you can see very well this B in B out will come here, what this will come here, see 2a square by 3, now 2a square by 3, 2a square by 3, and again see one more a square is there. Okay, so again see this a square and a square will cancel out, is it, so what is coming here, answer is coming here 2 by 3. Now so B in by B out, how much here, answer 2 by 3 is the answer. Can you see very well, now we have seen the ratio, we have to identify which point inside here, which observation point outside here. Now we are coming to hollow wire. Now this also sometimes they are asking, see here, magnetic field of a hollow wire. We have seen thin wire, thick wire, now which wire, hollow wire. So outside the wire, again I am telling you here, see here, if I will take here any point A outside here, now so see here I have taken the Amperian loop, now this I have taken point A here, and in the same fashion this is R, and let's take current is flowing here, now in this direction current is flowing here, let's take the current is flowing like this here, is it, and you know very well as this is the thick wire, the current will flow on the surface of the wire. Where the current will flow here on the surface, where the current is flowing on the surface of the wire. Hollow wire is there, hollow pipe, is it, where on the surface here. Okay, so anyhow there is the no cross section, I can draw here any cross section because it is flowing on the surface. Okay, so here also what will happen that here this magnetic field is like this, I will take here. Okay, and the DL also in the same fashion like this. Okay, and anyhow you can see the Amperian loop in which direction, this direction. So same story will be there, outside the wire, no change, it will be same, mu naught I by 2 pi r. Okay, derivation is not at all important, but same basic is there, na? Because inside the Amperian loop, na? See this is the Amperian loop, how much current is enclosed, anyhow the current is flowing on the surface of the hollow cylinder, but anyhow how much current is enclosed, I current is enclosed here. Similarly if I take any point on the surface here, see let's take I have taken any point here on the surface, and see here this distance I will make it a small r. Okay, so if in case the radius of this cylinder is capital R, small r equal to capital R, so B surface what will come here, we can write here mu naught I by 2 pi r, and whenever we are telling just surface means just outside, surface means nothing is mentioned here, just outside, okay, just outside. Now inside the wire is very interesting. Why? Because see if I take your observation point C here, see I am making observation point in a circle, see my observation point C is here. Okay, this observation point C is there. Here what will happen that here, see this distance how much here, this distance is smaller anyhow, so you know very well R is less than R, And if I talk about the magnetic field calculation, we can write as see B.dl is how much here? Mu naught in I enclosed. Very interesting. So see, anyhow see, B into same story, 2 pi R is equal to, any current is enclosed? No, current is not enclosed, because current is flowing where? Current is flowing on the surface. There is no enclosed current, no area of cross section, only surface. So here enclosed current will be how much here? This enclosed current will be 0, okay? And this only will make the magnetic field 0 inside the hollow wire. Inside the hollow wire, how much magnetic field? 0, okay? That means if I write here, see, if I draw the graph here, see, this is B versus R, like this it will go here. Like this is the B out, is it? And even this side also, if you want to draw here, this side also you want to draw here, like this you can draw in the same fashion, like this, okay? Inside any magnetic field is there? No magnetic field inside, because current is flowing on the surface, not inside, is it? So see this question, see how many years are there, see J 2004, 2007, 2022, even for the important for NEET also, see an infinite long hollow conductor conducting cylinder with a radius r carries a uniform current along its surface. See, along its surface, given even along its surface. The correct representation of magnetic field B as a function of radial distance small r from the axis of cylinder is. Radial distance means perpendicular distance, okay? So these 4 graphs are there. Even you can comment also. Which graph is correct here? Anyhow, you can see very well. The correct option is here, option D. Why? Because in this option, magnetic field inside, how much here? 0. Magnetic field inside, how much here? 0, because R is less than capital R. Inside, magnetic field is 0. And after that, if we write here the B outside is inversely proportional to R, where we can tell R greater than R here. Is it? So you can see the correct option is here. Option D is the answer. Is it? So students, I hope so. This video based upon Ampere's circuital law, its applications and questions is very, very clear to you. Keep studying, keep growing.